Splitting of signals. The splitting of NMR signals is an important aspect of the NMR spectrum, as it gives information about the neighboring protons. Let's focus on the NMR spectrum of this compound. So this compound should give us two peaks, one peak for the methyl protons and the other peak for the methyl protons. Right? The methyl protons are going to definitely appear in the upfield region, and the methyl protons are going to be in the downfield region. Right? But one important thing here to note down is the peaks of the methyl protons and the methyl protons are split. And they're going to be following the order n plus 1. The splitting pattern is going to follow this order n plus 1. The n right here represents the number of equivalent protons on adjacent carbons that are not equivalent to the protons that produce the signal. So which means if you take a look into the methyl protons will be split by the neighboring protons. So the methyl proton has got only one neighbor here, and that is the methyl proton. So there's the value for n is going to be 1 here. So 1 plus 1. Therefore, it will be split as a doublet. That's going to be equivalent to 2. So therefore, this is going to be split as a doublet. So the methyl protons are split by the methyl protons as a doublet. That is the meaning for this. So this is split as a doublet. Now let's take a look into the methyl protons. What should be the splitting pattern for the methyl protons? Now let's find out the number of neighboring hydrogens for this methyl proton. The methyl proton has got 3 neighboring hydrogens. That is from the methyl protons, right? So the value for n here is going to be 3, right? So 3 plus 1, that's going to be equivalent to 4. So when you say 4, the multiplicity of this is going to be quartered. So the splitting pattern of this is going to be quartered, which means you should see 4 peaks within this peak, 1, 2, 3, 4. So that would be the splitting pattern for the methyl proton.
So the splitting is going to follow the n plus 1 rule, and in some places we'll also be replacing this n plus 1 with Na plus 1 times Nb plus 1. The number of peaks that is present in a signal is called the multiplicity. Let's say that one signal has been split as 2 peaks, in which case we are going to call this as a doublet. When the signal has been split as 3 peaks, then it will be a triplet. 4 peaks will be called as a quartet. 5 peaks quintet, 6 peaks sextet, and after that we generally call it as multiplet.
Now let's also identify the splitting patterns for each one of these protons. By looking at this molecule, we can definitely say that there are going to be totally 3 signals, right? Because there are 3 sets of equivalent protons. So let's say that this is one set of protons, this is second set of protons, and this is going to be the third set of protons. Now this methyl proton will be split by the methylene protons as a triplet. Why? Because what is the number of neighboring protons for this methyl protons? The n value for n equals 2 because you have 2 neighboring protons here. So 2 plus 1, that is equivalent to 3, and therefore this should be split as a triplet. And let's go on to the next set of protons, the methylene protons. The methylene protons will be split as a quartet because you have 3 neighboring protons here. So which would be 3 plus 1, that's going to be equivalent to 4. It's going to be a quartet. Now let's go on to the third set of chemically equivalent protons. Now these hydrogens are not going to be split by anything as it doesn't have any neighboring hydrogens. So basically n is going to be equivalent to 0 and 0 plus 1 is going to be 1, which means this peak, the peak corresponding to these methyl groups, are not going to be split in any way. So this would be a singlet.
Let's do one more problem. Let's take a look into this compound. Here we have the CH3 protons. These 3 protons will be split by the methylene protons as a triplet because you do have 2 neighboring hydrogens. So n equals 2 and then n plus 1 equals 3, and therefore it will be split as a triplet. So this will be split as a triplet, and these 2 hydrogens also have got 2 neighboring protons, and therefore they will also be split as a triplet. This aldehyde hydrogen will not be split at all because it doesn't have any neighboring hydrogens, and therefore it will be appearing as a singlet. Now let's focus on these 2 hydrogens right here, this methylene hydrogens right here. So this one has got 2 different neighbors, 2 non-equivalent neighbors. Here you have 3 hydrogens from the methyl group and 2 hydrogens from the methylene group. And because they are non-equivalent, we are going to use a different formula. We'll be using Na plus 1 times Nb plus 1. We're going to assume that this is going to be the Na protons. This is going to be 3 plus 1. And here are the Nb protons. This is going to be 2 plus 1. So it's going to be split as a total of 4 times 3, which is equivalent to 12 peaks. Therefore, the peaks for these hydrogens will be split as a multiplet. But the actual number of peaks that you will be seeing in the spectrum is going to depend on the overlapping of the different peaks. It is important to remember that only non-equivalent protons split each other's signals, whereas equivalent protons do not split each other's signals. Now let's do this with two different examples. We have got bromomethane here, and this carbon has got 3 hydrogens. All of these 3 hydrogens are equivalent, and therefore they will not be splitting each other's signal. So here in this case, there will be only one singlet, which corresponds to the 3 hydrogens, all 3 hydrogens. Let's go on to 1,2-dichloroethane. We have 2 methylene groups here, but both of these 2 methylene groups are one and the same because there is a symmetry in this molecule. And because of this, they will not split each other's signals. Okay, so for this molecule, you will only be getting one singlet again, which corresponds to a total of 4 protons because both of these sets of hydrogens are equivalent.
Now, the next important question that we needed to answer is what causes splitting? Splitting occurs when different kinds of protons are close enough for their magnetic fields to influence one another, and this situation is called as spin-spin coupling. Spin-spin coupling. Now let's say you have this methyl protons. This methyl proton will be affected by the magnetic field of the methine protons. The magnetic field of this methine proton can align with the field or against the field. Let's say if it gets aligned with the field. If it's going to get aligned with the field, then it will add to the applied magnetic field. Therefore, B effective will be a large number, right? And therefore, it is expected to show a signal at a higher frequency. And this is the signal that corresponds to when the methine proton has its magnetic field aligned with the field. Now let's say that the magnetic field of this methine proton is aligned against the field. So in which case it will subtract from the applied magnetic field. The B effective will be a smaller number. The actual magnetic field that is experienced by this nucleus will be a smaller number, and therefore it is expected to show a signal at a lower frequency, which can be seen here. So this is the reason for the splitting. In general, let's say if you do not have any neighboring hydrogens, then the methyl protons are going to just appear as one singlet. But because it has got one non-equivalent neighboring proton, the magnetic moments of it can be aligned with the field or against the field, therefore giving rise to a doublet. Let's now focus on the methine protons. The methine protons will be split by the methyl hydrogens, methyl protons, right? So here you have 3 non-equivalent hydrogens, and therefore it will be split as 4 peaks. It will be a quartet. And here is the pattern for the quartet. It's going to be the ratio 1:3:3:1. Now, why we should have this particular ratio? Here again, it's going to depend on the magnetic moments of these 3 nuclei. The magnetic fields of the 3 protons can be aligned in different ways. Say, for example, you want the magnetic moments of all the 3 protons aligned with the field, then there is only one possibility. And similarly, when you want all the magnetic moments to be aligned against the field, then there is only, again, one possibility. But when you want to align 2 of it with the field and 1 against the field, then there are 3 possibilities. And similarly, 2 against the field and 1 with the field, there are again 3 possibilities. So, therefore, the signal is going to be split in the ratio 1:3:3:1. Following the same method, we should be able to find the splitting pattern for the rest of the peaks. For example, when you take a triplet, obviously it's going to show 3 peaks, and they are going to be in the ratio 1:2:1. And in the case of quintet, it's going to show us 5 peaks, right? And it's going to be the ratio 1:4:6:4:1. And this is the splitting pattern for sextet, and this is for septet. Remember, splitting is observed only if the protons are separated by no more than 3 sigma bonds. Now let's take a look into this first example here. The HA protons will be split by HB protons, and similarly the HB protons will be split by the HA protons because they are separated by 3 bonds, 3 sigma bonds, 1, 2, 3, right? But here in this case, the HA protons or the HB protons will not split each other's signals because they are separated by 1, 2, 3, 4 bonds. But splitting can occur through 4 bonds if one of those bonds is going to be a double bond. So let's say HA protons will still be split by the HB protons because they are separated by 4 bonds, and out of those, one of those is a pi bond. One of those is a double bond, right? And this we call as long range coupling.